Today we want to extend our momentum unit to a law that we call the law of conservation of momentum. We've said until this point that momentum can change. We've said that impulse is defined as the change in momentum. Momentum can be gained or lost. When you fire a bullet, the bullet gains momentum. When a car hits a wall, the car loses momentum. There's a change in momentum. There's an impulse. What I'm about to tell you, though, on the surface, contradicts what we've learned over the last few days. You'll see why in a few moments that it doesn't really contradict it, but on the surface it does. The law of conservation of momentum says in an isolated system, the total momentum will always remain constant, right? It's conserved. The law of conservation of anything says it's going to remain constant. Conservation of energy says energy remains constant. Conservation of mass says mass is going to remain constant. Conservation of momentum says momentum is going to remain constant. You can't create or destroy momentum. It's going to stay the same. So how do we justify the statement that I just gave you, having just talked about for the last several days, having just talked about change in momentum? How does momentum always stay the same, but yet momentum can change? Momentum can be gained or lost. I'll take you back to the video that I just showed you, okay, where Mel Gibson gets shot by the shotgun. When the guy fired the gun that shot that fired the buckshot that hit Mel Gibson, the total momentum of the gun / shot remained the same. It was zero. Okay, the gun and I was going to say bullet. The gun and buckshot had zero momentum before it was fired. It had zero momentum after it was fired. The total momentum remained the same. But let's take a look at the shot for a second, the buckshot. It gained momentum in the positive direction. The gun gained momentum in the negative direction. The total momentum remained zero. We can have a gain or a loss of momentum when we're talking about the individual objects within a system. But if we look at the system, the total amount of momentum will remain the same. Two football players hit each other. Okay, they're running, they collide, they hit each other. Each one of them will experience a change in momentum. One's going to gain, one's going to lose. But combined, the total momentum will remain the same. What have we been doing up until this point? We've been analyzing the individual objects within the system. Now we're going to start analyzing the bigger system and say that the total momentum remains the same. It's conserved. What do we mean, by the way, by an isolated system? What does that mean? Yeah. Yeah, there's no outside forces. Let's say no external forces. I mean, think, if you got friction and you're not taking the friction into account, well, then you can lose momentum, right? The total amount of momentum will decrease. But if you have no external forces, nothing that's causing it to speed up or slow down beyond the interaction itself, then the total momentum will always remain the same. Now, we're going to use this to solve collisions and what I call explosions, although we don't necessarily mean literally an explosion by that. Could be. A bomb goes off and pieces go everywhere. We could analyze that using the law of conservation of momentum, but it could be something as simple as firing a gun. It could be something even simpler. You're standing on ice, you got a heavy ball, you throw it, the ball goes one way, you go the other way. When one object, which would be the bomb or the gun and the bullet or the guy on the ice and the ball, when one object becomes two, it's like an explosion. So when two objects collide, two things come together, or one thing splits apart into two or more objects, then we can use this law of conservation of momentum to deal with it. And we kind of addressed this already. The total momentum in an isolated system stays the same. That doesn't change what we've been talking about for the last few days, that the momentum of individual objects can change and will change. But if two things collide and one gains 5 units of momentum, well, then the other one's got to lose 5 units of momentum to keep the total momentum the same. Now, when we did impulse, we started off deriving an equation for impulse, which you don't have to remember the derivation, by the way, but the derivation came from Newton's second law. Remember, F is equal to m times a? Remember, we subbed in delta v over delta t for acceleration, and we ended up getting F times t is equal to m times delta v. Impulse comes from Newton's second law. F is equal to m times a. Conservation of momentum actually comes from Newton's third law, which says that the force of one object acting on another is the same as the force of the second object acting on the first, equal but opposite. You don't need to remember this derivation either, but I'm going to give it to you. In the end, what you need to remember is the final product, what we get at the end of this. We're going to say that F12 is equal to negative F21. That's Newton's third law, right? The force of object 1 on object 2 is equal and opposite to the force of object 2 on object 1. We're going to replace F with m times a. Mass of object 1, acceleration of object 1 equals negative mass of object 2, acceleration of object 2. Agree? Still Newton's third law. We're going to replace a with delta v over delta t. So m1 times delta v1 over delta t1 equals negative m2 times delta v2 over delta t2. All I've done is subbed in delta v over delta t for acceleration again. I'm going to cancel out the times. How come I can do that? It's two different times, right? Delta t1 and delta t2. How come I can cancel out that time? Good, man. So we can cancel them because the times are the same. The time of collision between object 1 and object 2 is the same. Object 1 collides with object 2 for 0.2 seconds. Object 2 collides with object 1 for 0.2 seconds. Different symbol, same time. So now we've got m1 times delta v1 equals negative m2 times delta v2. I want you to take note of this before we go any further with it. M times delta v is equal to what? M times delta v is equal to, we've already done this, delta p, impulse, right? So we're going to say the impulse on number 1 is equal and opposite to the impulse on number 2, and that should make sense, right? If object number 1 gains 10 units of momentum, then object number 2 has to lose 10 units of momentum in order to keep the total momentum the same. All right, let's go a step further here, though. Let's replace delta v1 with vf1, or v1f, we'll call it, v1f minus v1I equals negative m2 times v2f minus v2I. Hold on one second here. Do a little bit of math. I'm going to skip a couple steps here just because the bell just went. And we end up with, and again, don't panic about the derivation of this anyways, just the final product. We end up with m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. This is important. What does this tell us? It tells us that the total initial momentum, right, the initial momentum of object 1 plus the momentum of object 2, the total initial momentum will be equal to the total final momentum, object 1 plus object 2. All comes from Newton's third law, right? F12 is equal to negative F21. Total momentum remains the same, which is what we just said over the last 10 minutes. Okay, the law of conservation of momentum says the total momentum remains the same. Okay, we'll pick this up where we left off here next day.